All right, so we're talking about internal loads, and we have talked about problems where all you have are point loads. Did anybody work on that daily assignment problem yet? Did that go okay?
Yes.
Okay. So now we're going to talk about what happens when there's distributed loads, and that's a pretty important topic because, for one thing, weight is a distributed load. Oh, wait, before I start this, exam 2 is a week from Friday. So I think that's November 4th. And there's going to be a quiz on Monday, this upcoming Monday. So, you can skim your notes, get ready for the quiz on Monday, and that'll help you as you start getting ready for the exam. Okay, so why is it important to be able to deal with distributed loads for internal loads? Because once you start doing internal loads, the distinction between equipolant systems and the true systems are important. And weight is actually not a single point force acting at the center of an object. It's actually a distributed load acting over the whole thing. So if we want to treat weight, which is a pretty commonly occurring force, if we want to include weight, we have to be able to treat distributed loads. So, okay, so now we're getting into internal loads in beams with a distributed, this is a long title, distributed load Q of X. Okay, so, for example, just talking generally, we'd be talking about a beam that's supported somehow. I'm just going to draw this. And then there's a distributed load like this. Where the value of that distributed load at any x is called a function Q of X. And we're going to use the common sign convention that down is positive. And the key idea is for each cut, we're only going to include the part of Q of X that acts on the isolated part. Okay, so in this example I just did, that I just drew above there, you'd have some cut like this, and this part of the beam that's not included. And when you do your cut, this stuff is included in your free body diagram and Newton's laws. and the light blue stuff is not included. And then for that cut, now that we've figured out what part is included and what part isn't, then you treat that distributed load as a point force. Now you come up with the equipolant system. But you can't do that until after you've taken the cut. And one thing that you have to remember, and I'm going to keep reminding you, but this is an easy thing to mess up. In finding the points where the subfunctions change, remember T and V and M are all piecewise functions, and we have to divide it up into cuts to calculate the individual subfunctions. In finding the points where the subfunctions change, the point forces used to represent the distributed loads don't actually exist. Okay, so like if you have a beam that has a weight acting on it, you're used to applying the full weight force at the center of the beam. But if you think of that as one of the places where the subfunctions change because you think of it as a point force, then your answers are going to be wrong. Okay. Instead, you have to think of that as a distributed load with a function that doesn't change over the whole length. And I'll give at least, we'll see how far we get, but I'll do at least one example like that. Okay, so I'm just going to get into a couple examples. There's really not much more to how you're supposed to think through this than what I've given here. I didn't give very much. And I'm going to start with a weight force, a rectangular distributed load, and then after that I'll go to a triangular one. So I'm going to start with weight, which is a rectangular distributed load. And so here's the problem. We have a beam with a pin joint on the left and a roller on the right. And the mass is 30 kilograms. And the length of the beam is 2 meters. And we want to calculate the internal loads. Well, just like with any other problem, the first thing we have to do is calculate the reaction loads, the external loads. So let's see what's going on here. At the pin joint, we have a force vector, I'll call it RA. At the roller, we have a force with a known direction, I'll call it RB. And I'm going to start out by defining this distributed load because we haven't dealt with weights this way yet. Since this beam has the same thickness everywhere, that weight distributed load is the same everywhere. How do we figure out the value of that distributed load? Well, we know that the total weight is 30 times 9.81. And we know that the length is 2 meters, so we're just taking 294.3 and dividing it by 2. And that's our function Q of x. Okay, it's a very simple function. It's just a constant. But it's a function, in general, that's a function that could vary with x. And now that we've chosen what body to isolate, now, so it's important that you don't do this until you choose the body to isolate. But now we can define the equipolant system and treat that weight force as a point force. So I'm going to write this out again. We have those same reaction forces at the end, RA and RB. And then, well, what can we say about that distributed load? It has a height of 294.3 divided by 2. Yeah. Yes, it should be. Okay, so the length of this whole thing is 2 meters. The height is 147.15. And so the area, that's going to be the value of the point force, is 294.3. And the centroid is at the middle. We didn't really need to calculate that because we've done this a million times. We just do it in our head. But I'm just showing you this explicitly because this is what we're going to do once we come to the cut. Okay, so we have a weight force of 294.3 acting right at the middle. You with me on that? Okay, so Newton's second law says RAX, RAY plus 0, negative 294.3 plus 0 RB is equal to zeros. And the moment equation, I'm going to use the about point all the way at the left. So the 294.3, this thing has a total length of 2 meters, so there's a moment arm of 1 meter for that point force for the weight. And would that make it rotate clockwise or counterclockwise? Clockwise, so that's negative. And then, well, I'll do the sign in a second. Moment arm of 2 for the reaction force RB. Would that upward force RB make it rotate clockwise or counterclockwise? Counterclockwise, so this is positive. And all this is 0. So RB is 147.15. And RA is 0x 147.15 for Y. Okay, so now I'm going to draw a free body diagram again of the whole thing now that we know everything that's going on. So we have 147.15 here, 147.15 here. And then the real actual loading that's happening is there's this distributed load, Q of X, that's equal to 147.15 newtons per meter. Okay, so now that we have the external loads, now we have to figure out where the subfunctions of those internal loads can change. So what are the criteria for choosing those points where you change the cut? Well, the endpoints, and then there are two other possibilities. Point loads, yep, point forces or point couples. And then second is where distributed load functions change, where this function Q changes. Does it change anywhere? No, it's the same. So Q of X doesn't change. So N is equal to 2, and that means that we only need one cut. Okay, so cut 1 is the only one we're going to do, and it's valid for all x's from 0 to 2. Okay, so we have an upward force of 147.15. We have this part of the distributed load, but not all the rest of this stuff. We have our internal loads. And the length of this piece is x. And our Q function is 147.15 newtons per meter. And now that we've chosen the piece to isolate, now we can represent that distributed load as a point force. So let's think about, that rectangle. Its width is x. Its height is 147.15. So the centroid is going to be in the middle. And what's the area of that rectangle? This is the point force. Yeah. So A is 147.15x. First time we've ever seen this. The force that we're going to apply from that distributed load depends on what x is. Okay. And now I'll redo that free body diagram, but with the distributed load replaced by that point force. So we have an upward force of 147.15. We have a downward force at the centroid of that rectangle, so here, with a magnitude of 147.15x. we have our internal loads. This distance is x over 2. This distance is x. And now we're doing everything exactly the same as we always did for internal loads. We just had some x's in there instead of numbers. So Newton's second law says 0, positive 147.15 plus 0, negative 147.15x plus t negative v is equal to 0. So t is 0 and v is negative 147.15x plus 147.15. And then the moment equation, the about point is going to be here like always. So there's no moment from the point at the left end. There is a moment from that weight force with the x in it, and the moment arm is x over 2. You see that? So we have x over 2 times 147.15x. And is that a positive or negative rotation? It's clockwise, so it's negative. And then all we have left are those internal loads. Those always show up the same way, plus m minus vx. So m is equal to vx plus 147.15x times x over 2 is 78 point 70. What is that? 78.58. 58? 5. Yeah, that seems right. Okay, thank you. 73.58 x squared. Right? And then now we can plug in for v. So m is equal to, we have to take what's in v here and multiply it by x. So negative 147.15 x squared plus 147.15 x plus 73.58 x squared. And then add up all the x squareds and you get negative 73.58 x squared plus 147.15 x. So what does that look like? T, we don't really have to plot. That's just 0 the whole way. What about the shear force? Okay, so when x is equal to 0, it's positive 147.15, right? When x is equal to 2, it's negative 147.15, and it's linear. So the shear force is going to look like this. And then the bending moment. Well, when x is equal to 0, that's 0. When x is equal to 2, that's also going to be 0. I won't tell you how I know that. Can someone plug in x equals 1? Oh, that's easy to do, isn't it? That is positive 73.58 at the midpoint. And so this is going to be a parabola, yikes, like that. So a couple things about this. We haven't seen any nonlinear functions yet up until now, but that's because of the distributed load. You're going to get that quadratic bending moment. As far as where this beam, we're worried about it breaking. It's not a single story really anymore. You can see that the absolute values of the bending moments are biggest at the endpoints, and the absolute value of the bending moment is biggest in the middle. So it kind of just depends. We'd have to do more analysis than we can do here. What about the derivative thing? Remember the derivative thing? dm dx always, for every x value, has to be equal to v. Okay, so dm dx is equal to negative 147.15x plus 147.15, and that holds. So that gives you confidence that you didn't make a mistake in doing this. One more thing. So we know that dm dx is equal to v. Look at negative dv dx. Why would you do that? I don't know. But negative dv dx is positive 147.15. Okay. And that is equal to, if you go back to the top, our q. And that's always true. So dv dx is equal to, or negative dv dx is always equal to q. Think back to the examples that we did before, with no distributed loads. What's q of x if you don't have a distributed load? What's the function if, 0? Yeah, it's 0. Q of x is 0. And think of the shear forces that we've seen. They've always been constant functions, piecewise constant. And so you take the derivative with respect to x of a piecewise constant thing, and you get 0. So it's always been true. We just didn't ever talk about the distributed load before. Any questions about that? This is all stuff that, so if you just remind yourself that what you're doing is exactly the same as what you did for rigid body problems, then you can work your way through all this stuff. It's just now variables are appearing in it where there always used to be numbers. Okay, so now I'm going to do an example with a triangular distributed load. So let's have our beam have a roller at the middle and a pin joint at the end. And let's say that here we're applying a force of 500 newtons. And our distributed load looks like this. Let's say that the magnitude of it is 2,000 newtons per meter. And I'll say each one of these is 1.5 meters, so the whole thing is 3 meters. And we want to calculate the distributed loads. What's the first step? Yeah, first we got to get the external loads. So I'll do a free body diagram of the whole thing. Last time, just sort of trying to emphasize the step going between the distributed load and the point force. I first drew this out with the distributed load on it and then went from there. This time I'm just going to jump just to how, this is just a rigid body problem. So I'm going to just do it like we've always done rigid body problems. I guess let's look at the shape so we can figure out the centroid and the area. So the length of this whole shape is 3. The height is 2,000. So the area is 3,000. That's going to be our point force. And our centroid is 1/3 of the way from the right toward the left. So this is 1 meter. And we have the 500 here. The 3,000 here. At the middle, we have the upward force, I'll call that RA. And then at the right end, we have the unknown vector that I'll call RB. Probably you would think of this as a problem with no weight in it, unless, you could think of the density as changing according to that function or something, but normally the weight is always going to appear as a rectangular distributed load. You can have more than one distributed load, and you can treat everything, break it up into 2 different pieces, calculate the point force representing each one of those. And then at the end, your Q function is just the sum of those 2 functions. But we're just going to do the one for now. Okay, so Newton's second law says -500, 0, plus 0 RA plus 0, negative 3,000, plus RBX, RBY is equal to zeros. And the moment equation, I'm going to put my about point here. It would save us a little work if I put it at that RB, but I'm just going to keep being consistent. I think the more consistent you are, the less dumb mistakes you make. So no moment from the 500. What's the moment arm of RA? 1.5. And is that positive or negative, that moment? Positive, yep, counterclockwise. And then we have the downward force of the 3,000. What's its moment arm? Nope, that's the one that's the centroid of the triangle. 2, yep. So 2 times 3,000. And is that positive or negative? That's negative, clockwise. Yep. And then there won't be any moment from RBX, but from RBY there is. What's the moment arm for RBY? 3. You can tell it's that because I was starting to write it. And then, so RBY, and then is that positive or negative? Positive, yep. Is equal to 0. Okay, well, now we got to do this with stupid reduced row echelon form or something, because that's what I get for not putting my about point at B, but I stand by it. Okay, so we got one, two, three, RA, RBX, RBY, and the constant. So for the first equation, we have 1 RBX, and the constant is 500. For the second one, we have 1 RA, 1 RBY, and the constant is positive 3,000. And then for the third equation, RAs, we have 1.5. RBYs, we have 3. And the constant is 6,000. Can someone calculate that for me? I'm going to pause this.
So RA is 4,000, RBX is 500, and RBY is 1,000.
500, 1,000. Anyone else get anything different? Your answer matches mine for RBX. No. 2,000? And, oh, okay. Well, RA. Yeah, it has to be 2,000 and 1,000. Okay, I'm going to go with this. Okay, so this is a step that, you can feel free to skip as you get comfortable with this stuff. But now I'm going to draw the complete free body diagram before we go on. So we have an upward force of 2,000. Over at the right end, we have an upward force of 1,000 and a force to the right of 500. We have the 500 to the left over on the other side. And now I'm going to, instead of drawing in the point force that represents this, just to sort of emphasize that that's not a real force, I'm going to put this thing in. Okay, so this is a finished free body diagram of the full body. And now we can use this to figure out how many cuts we're going to need. Notice that if you used this free body diagram of the whole thing to figure out what cuts you needed, you'd think that that 3,000 was a real force and it would mess you up. So how many places are there where the subfunctions could change? The two endpoints, and then there's a real point force at the roller. Yep. So N is equal to 3, and that means this time we're going to need 2 cuts. The distributed load function is the same everywhere. And before I go into the internal loads, before I go into the first cut, let's think about what that Q function is. Okay, it was a constant function last time. What is it this time? You can see it's not constant. Well, you can see that if we think of it as, it's just a line, right? So we just need the equation for that line. The slope is going to be, it goes from 0 to 2,000 over a distance of 3. So the slope is going to be 2,000 over 3, which I guess is 666.6s. And the y-intercept when x is equal to 0 is 0. So that Q of x is positive 2,000 over 3, or 666.67 this times x. It's a linear function. Okay. Okay, so let's do the first cut. This is valid for any x's between 0 and the first place where the subfunctions change is x is equal to 1.5. So x here is between 0 and 1.5. And here's the free body diagram. So we have this force here that doesn't really occur. I mean, it really occurs, but it's not on our the piece that we're isolating. We have these forces that aren't included. We do have this 500 over here. And now here is the thing that's going to be kind of a pain. Like, look at this distributed load. Okay. Up here, the height of this triangle is 2,000. But what's the height of the triangle that's included in our part? You know, because we can't calculate the area without that height. Yeah, it is, exactly. So, you know, notice that this distance is x. And so the height of that triangle is just our Q function, right? Because you're plugging the x value into to get the height. So over here, we just have 666.67x. Now to do the calculation, we have to represent that distributed load as a point force. So let's think about that triangle. Its width is x. Its height is 666.67x. Centroid is 1/3 of the way from the right towards the left. So what's this distance? Yep, exactly. So I'm going to redo the free body diagram now with that point force in there. We have the 500. Oh, there's no upward force there. Then we have the downward force from the distributed load. Oh, I didn't calculate that area. So what's that area going to be? 666x times x divided by 2. So 333.33 x squared. And then T, V, and X, M. And this distance is 2x over 3. So now Newton's second law says negative 500, 0, plus 0. Okay, now this messes with people's heads all the time. What's the sign of this 333.33x squared is in the y direction only. Is it positive or negative? It's negative. Think of that as the arrow is a unit vector and you're multiplying it by a number, okay? So 0, 1 times that. So this is 0, negative 333.33x squared. And then plus t minus v is equal to zeros. So t is 500. V is negative 333.33 x squared. And now the moment equation. We have a moment arm of 2x over 3 times this force of 333.33x squared. Is that a clockwise or counterclockwise rotation? Clockwise, so it's negative. And then plus m minus vx is equal to 0. So m is equal to v times x plus 222.22 x cubed. And now substitute in this v, and we get m is equal to negative 333.33 x cubed plus 222.22 x cubed. And so m is equal to negative 111.11 x cubed. Okay, that's only our first cut. I'll have to finish this on Friday, but because you multiply the v function times x. So here's something that if you're paying attention to as you do these problems enough times, eventually will occur to you. Doing the moment equation was kind of a pain. I know there's this derivative relationship between v and m. What if I just take this v and integrate it to get m? You know, it does work. And you can do it that way. It's not really any easier though, because the thing that you have to come up with is boundary conditions, and you end up messing around to find the boundary conditions as long as it would take to do this. And so either way, you would do it one way and use the other way to check your answer. So I just do it this way. But you can see that the derivative relationship holds. If it didn't hold, it would mean we had to do this all again right now. And it's very depressing when that happens. Any questions? Okay, that's it. So I'll finish this next time. Let me leave you with one additional thought before we go, something to stew over actually. What about what if our beam was like this? You know, here's the distributed load. Would that be about the same to calculate? This actually would be a super huge pain, because when you go to do your cut, notice that shape isn't a triangle anymore. The part that makes it a triangle is left over here. It's a trapezoid. Okay, so you'd rather not do that. So what I recommend doing instead, if you have a problem that looks like this, is imagine yourself walking around the end to the other side and looking at it, and then just do that problem. Okay. You can do this, but it just takes way longer than it needs to take, you know. Okay, that's all.